Here on the board, you can see 10 questions about the governing equations for the flow field, or the Navier-Stokes equations, and the constitutive relations. Question number 1, this is the flow field. Compute the acceleration of this flow field using the material derivative concept. Question number 2, is this flow field viscous? In other words, compute the viscous term in the Navier-Stokes equation, assuming the properties to be constant, the properties such as viscosity to be constant, and also Newtonian fluid, for a Newtonian fluid. Question number 3, compute the pressure field for this velocity field using the Navier-Stokes equations. Question number 4, where is the stagnation point of this field, or what is the coordinate of the stagnation point for this velocity field? Then you can compute the stagnation point pressure using the result in section 3. Question number 5, calculate the strain rate tensor, again for this velocity field. Question number 6, compute the stress tensor using the Stokes relation for this velocity field. Question number 7, what is the magnitude of the mechanical pressure? And then compute the mechanical pressure with the thermodynamic pressure. Question number 8, you can see two streamlines. These two lines are streamlines, and suppose that both of them are a part of a circle, so that the radius of curvature at different points along these streamlines is a constant. Then, question number 8, compare the pressures at points A and C between two streamlines. Suppose that you can use the Bernoulli's equation, and basic assumptions behind the Bernoulli's equation are all valid here. So compare the pressure of point A and C between two converging streamlines. Then compare pressures of points B and A. Question number 9, compare the pressure difference between points D and C and the pressure difference between points B and A. Which pair of points has a larger pressure difference between 2 points? Question number 10, compute the Mach number at points 1 and 0 for this velocity field, and suppose that the fluid is air at a standard temperature and pressure. And also assume that the value of the constants alpha and beta is 10 inverse of second. As you see from this relation, the dimension of alpha and beta should be the inverse of second, or the inverse of time, because of the dimensional homogeneity. The answer to the first question, what is the acceleration of this velocity field? You have to write the material derivative operator in 2 dimensions. This is the acceleration in x direction. The next one is the acceleration in y direction. The first term denotes the time derivative or the local derivative. And the 2 next terms are the advection terms, or the nonlinear terms. Okay, just substitute these relations in the material derivative, and this is the final results. We have 2 terms with opposite signs, which cancel each other. The answer to the second question, is this velocity field viscous or inviscid? You have to compute the viscous term, the Navier-Stokes equation, which equals the Laplacian of the velocity field if the viscosity is a constant. So the Laplacian of this velocity field is 0 because all terms are linear and the second derivatives of all terms will vanish. So this flow can be regarded as inviscid flow because there is no trace of viscosity in the Navier-Stokes equation because the Laplacian of the velocity is 0. The answer to the third question, the pressure field, you have to write the full Navier-Stokes equation. This is the acceleration term obtained in section 1. This one is the viscous term obtained in section 2, which is 0. And this is the body force, which you may keep it in the relation or ignore it, no difference. I have ignored this term here. And the pressure gradient term equals the pressure derivative, the partial derivative of P with respect to X and Y. So substitute these results in this relation and integrate with respect to X and the second time with respect to Y. You will obtain two expressions for pressure and two constants of integrations. The first one is a function of y, and the next one is a function of the other function of x, f prime, for example. And then both of these relations are pressure, so they should be identical. And then consequently, this function of y should be this relation, and the f prime, which is a function of x, should be this relation. So the pressure is the sum of these relations plus a constant such as P sub 0. Question number 4. Where is the stagnation point of this relation? The stagnation, the velocity at the stagnation point is 0. So both velocity components should be 0. And as you see here, this one is equals 0, and the next one is also 0. We have two equations with two unknowns, and the determinant of the matrix of coefficients and coefficients of this system of equations is non-zero, and the second right-hand side, of both equations are 0. So the only answer to this equation is 0 and 0. So the origin of coordinates is the stagnation point, and then you can substitute this relation in the expression for pressure and find the pressure of stagnation point. Question number 5: compute the strain rate tensor. This is the expression for the strain rate tensor, which is a symmetric tensor. Partial derivative with respect to x, partial derivative of u with respect to x, which equals alpha. Similarly, the partial derivative of v with respect to y equals minus alpha. And half of sum of partial derivatives of u and v with respect to y and x respectively, which equals beta plus beta all over 2, or beta, simply beta, which is a symmetric tensor. Question number 6. Compute the stress tensor by assuming the fluid to be Newtonian. This is a linear relation between the strain rate tensor and the stress tensor. This is the hydrostatic pressure. This is the Kronecker delta, the first coefficient of viscosity or the dynamic viscosity. This one is the contracted form of the strain rate tensor, or which equals the divergence of the velocity field. The second coefficient of viscosity, or the bulk viscosity, and again the Kronecker delta. The last term in the relation is 0 because the velocity field is incompressible and its divergence is 0. And so in matrix form, stress tensor equals minus p minus p minus p, a diagonal matrix, plus twice viscosity, and the strain rate tensor, similar alpha minus alpha, alpha minus alpha, beta beta. The other components of the matrix are all 0. So this is the final form of the stress tensor, which is again a symmetric tensor. This part is called the viscose stress tensor. The second matrix here is the viscose stress tensor, and the first matrix is called the hydrostatic stress. It's obvious that in our case the viscose stress tensor is non-zero, is not zero, but the viscose term in the Navier-Stokes equations is zero. Question number 7. Compute the mechanical pressure. As you know, the mechanical pressure is minus average of the diagonal components of the stress tensor. So you have to compute the average of the diagonal components, or compute the trace of the stress tensor and divide it by 3 to compute its average value, and then add a minus sign here. So the numerator of this relation shows the trace of the stress tensor, and this 3 here means that this is the average of the diagonal components of the stress tensor, and because it's the mechanical pressure, so we have to add a minus sign before it. And you see here we have 2 terms with opposite signs which cancel each other, and then here we proved that the mechanical pressure equals the thermodynamic pressure, which was so obvious because the flow is incompressible. Question number 8. Here we have 2 streamlines, and based on the Bernoulli's equation, because the streamlines are convergent, so the area between the streamlines reduces. So the velocity of point A, due to the continuity equation or the conservation of mass, the velocity of point A is greater than the velocity of point C, and based on the Bernoulli's equation, the pressure of point A is less than the pressure of point C. Also from the Navier-Stokes equations, which by neglecting the body forces and also by neglecting the viscose forces, this relation can be obtained, which is called the Euler Equation. This relation shows the variation of the pressure in the normal direction to the streamline, and the other side of the equation is velocity squared over the radius of curvature at that point. For points, for example, A and B, as you see, the second hand side is a positive number, so the pressure increases in the outward direction, in the outward radial direction, so the pressure of point B is greater than the pressure of point A, because the second hand side is a positive number. Similarly, the pressure of point D is greater than the pressure of point C. Question number 9. Compare the pressure difference between points B and C and the pressure difference between points A and B. Again, referring to the Euler's equation, the radius of curvature of the streamline at points A and C are equal because the streamline is assumed to be a circle. And but the velocity of point A is greater than the velocity of point C. So the pressure gradient at point A is greater than the pressure gradient at point C. So the pressure difference between points A and B is greater than the pressure difference between points B and C. The last question, compute the Mach number at point 1 and 0 for air at standard temperature and pressure, assuming alpha and beta being equal to 10. So you have to first compute the velocity vector at points 1 and 0 based on this relation, and then compute the magnitude of the velocity vector at that point, which equals approximately equals 14 meter per second. And based on the definition of the Mach number, the Mach number equals the ratio of the velocity magnitude and the velocity of sound. The velocity of sound for a perfect gas, calorically perfect gas with constant properties, equals root square of product of gamma, or the specific heat ratio, the gas constant R, and the temperature, the absolute temperature. For in our case, equals approximately 343 meter per second. So the Mach number at this point, at this specific point, equals 14 over 343, which equals approximately 0.04. As you see, the Mach number is very smaller than the limiting Mach number, which is 0.3. So as you see here, the divergence of the velocity here is 0. So it means that the velocity field is incompressible.